pleasure to introduce Carlos da Mota. He's going to talk about Cauchy problem for combustion model in porous medium with several layers.
Thank you for your presentation. I am very happy to be here. These honors to Professor Dan Marchesin. I am one of the first doctoral student of the Marchesin. I am very great. The first one? Yes. Okay. One of the first. Okay. I am very happy for this. This is the topics of my talk. We spend a little words with the model. Then we state the Cauchy problem we are talking about. We define the upper and lower solution. Then we present the iterative method of the monotone sequence we are using to solve the Cauchy problem. And then we present our main results about local and global solutions in time of the Cauchy problem. And finally, some comments. Here we have a list of some articles related to combustion in porous media, only some papers. There is a vast literature in this area. The model, our model consists in a porous media with several parallel layers like this, each one with different physical properties, okay, filled with fuel and air. We consider that the heat transfer only between two neighboring layers, okay? And there is no loss heat to the external environment. We have this equation. The following equations are assumed to hold in the ice layer and layers, okay? One equation for the balance equation, balance fuel mass, balance of oxygen mass, balance of gas mass, and Darcy law. After manipulating these equations, we can decouple this set of equation with this other set of equation, and then we obtain a more simple model. Okay. This is a kind of Arrhenius law we are using, like that similar Shapiro used yesterday. Okay. After some simulation, that two set of equations are coupled with only this term. So, only this term. So, considering an average value for this value, we can decouple some equations, obtaining a model including only temperatures and fuel concentration. We denote the temperatures by UI and the fuel concentration with YI. Okay? The model after simplification, we have these equations for temperatures and this equation for the concentrations, where these values are non-negative constants. Okay. Some one are positive constants, like A, B, and these A are positive constants. We rewrite the system of PD equation using this differential operator and this reaction function. This is not the reaction function really. The reaction function is this term, because this function f is the reaction function. This is the term of retransfer from one layer to the other. Okay, that's okay. One important thing that occurs is that the differential operator is uniformly elliptic. It's important to obtain convergence of the method. The Cauchy problem for temperatures. Okay, that's okay. We have a simplification hypothesis, field concentration yi as non-function. We consider in this problem the field concentration as a bounded non-function, like here. So the model was simple. Okay, so we have this following this set of equation: layer 1, layer between 2 and 9 minus 1, and layer n, because this function is different in these three equations, and the initial data. Okay. We look for a solution, local solution in time for a classical local solution to continuous derivative with respect to x and continuous derivative, first derivative with respect to t. Okay, and global solution in the classical global solution too. Okay. For n equal 2, we have a paper here. Okay, the monotone method of upper and lower solution is a good reference for this. Okay. We are dealing with functions u, including the case ux, on the set satisfying the growth condition, this growth exponential condition. It is because the domain is unbounded. The domain is R for the variable x. Okay. We put the system in vectorial form using this equation. So we have a system like this, where G is we call this G is the source term. Okay. Upper solution is usual definition of upper solution. Okay, satisfying the growth condition is the definition of the lower solution, also satisfying the growth condition. We need this growth condition to obtain convergence because the domain for x is unbounded. Okay. The first lemma, let t, capital T, be any positive number, and assume that the initial data are non-negative and bounded function, bounded on R. So 0 is an lower solution. We can see that exists. You see that 0 is a lower solution for the problem, and this function here with the same components, each component like this is an upper solution of the problem. It's easy to see it. Substitute this in the partial differential equation and prove that this is a an upper solution of the problem. Okay? And this solution, this lower and upper solution satisfying the exponential growth condition. Next, we construct the monotone sequence of upper and lower solution and prove their convergence for the unique solution of the Cauchy problem. For n xt in this domain, our iteration at the point xt will take values in a sector of functions. This sector of functions, this is, we have to look this component by component, okay, these inequalities, component by component. A good property for the system is that this g function is quasi-monotone non-decreasing function. Means this inequality. This is this definition of quasi-monotone of this the source function. Okay, and g satisfies the Lipschitz continuous condition uniformly in xt. We are right. We need that the function, the source function, to obtain convergence. We need that the source function need to be monotone, non-decreasing function with respect to the variables temperatures. So we have to add some terms in both sides of the equation to obtain this condition. The term added in both sides is Ku. So we obtain this new Cauchy problem with these properties, with this property, okay? So we define the following iteration for the problem. We start with an initial iteration, okay, and define this. We know the solution in a level k minus 1 to obtain the solution in a level k of the iteration. Okay, we start so with this method. We can construct two sequences of lower and upper solution. For the lower solution, we start with the lower solution, 0. We become the first iteration has to be the lower solution. And we construct the other sequence of upper solution starting with the upper solution. Okay? So we construct two sequences of lower and upper solution. The local solution, assuming that the initial condition are non-negative, continuous, and bounded function on R. Concentration, the concentration yi are bounded, non-negative, and Holder continuous function in this domain. Then the sequence of upper solution and the sequence of lower solution converge to the unique solution U in the classical sense of the Cauchy problem, modified by that K. Each component satisfying the growth condition. The proof of this theorem is based on, we have to prove for each iteration that we have that the sequence of lower solution is increasing with the iteration. And the sequence of upper solution is decreasing. Okay? And both are, and all these sequences are bounded below and upper by this function. So, pointwisely, we have convergence of this sequence. Okay? So we can prove that this sequence of upper solution converges to a function, and this sequence of lower solution converges to another function, and we can prove that these two functions, okay, are the same, coincide. To prove this, we have to use an integral representation of the solution, okay, because this system here now is linear, because we know this function. The system is linear, so we have an integral representation for the solution of this system using fundamental solution. Okay. So we can prove the unicity of the problem. Okay. For global solution, the same hypothesis. Okay. In this initial condition are non-negative continuous and bounded function are. Concentration are bounded, non-negative and Holder continuous function in this set. Then there exists a unique solution U of the problem, of the Cauchy problem, in the classical sense, such that the solution satisfying these inequalities. Okay. Furthermore, the sequence converges pointwisely to the unique solution U. Okay. The proof of this theorem is that for each t, this sector of functions, for a minute, thank you. For each t, this sector of functions, we have a unique solution in this sector for each t fixed. So, if T2 is bigger than T1, we can consider a natural inclusion of this sector of function in this sector of function when T is bigger than 2. Okay? Then by the restriction map, thus we obtain a solution U in this by defining the unique sequence solution in this set for nt bigger than 0. Okay? So we have a unique natural extension of the local solution to the global solution. Here we more reference here. Okay. This is the article with for n equal 2, the same problem. Happy day this now. Thank you.
Any questions or comments?
Yes, smooth condition
Smooth dependence on initial conditions.
with depend.
Smooth dependence.
Yes. Okay.
Con relación a las condiciones iniciales.
No, we don't have this. We don't answer this question in my problem. Okay, in the problem, we won't find a unique solution. Okay, we don't unique solution.
But you have a choice of solutions which is smooth dependently on the initial.
No, we don't have this result. Okay.
You don't consider this.
No, we don't.
Is it false?
No, I don't know it's false. I think it's true, but they don't prove this. Okay? Initial condition. Okay.
I got a little confused about how much coupling there is in this system. Are these completely uncoupled?
Okay, let me show you. In this one or in the first?
So this is the one you proved the existence here?
Yes, this.
And the first one?
Oh,
is
yes, this. Okay, okay. This is for the first layer. The couplet is in this term here only. Okay, this term here, because this here is its variable, its temperature. This U is 1, 2, 3, etc. Okay, the couplet is here. Okay.
Any other question, comment? Then let's thanks Jesus again.
Thank you.